Welcome back, everyone. We will now get started with the main seminar of this week, which will be given by Josse van Dobben Bruyn from Charles University on asymmetric graphs with quantum symmetry. Take it away.
Thank you. Thank you for the introduction and for the opportunity to speak in your lovely seminar. And we'll be talking about asymmetric graphs with quantum symmetry. This is joint work with David Robertson in Denmark and Simon Schmidt in Germany. And I mentioned here the DOI because it got published exactly a week ago now, which we're very happy with in the proceedings of the LMS. So that's great. Right. So what is this about? So I'm gonna first give a brief introduction about quantum isomorphisms and quantum automorphisms of graphs. Then motivate the definitions that I give from two perspectives. One of them is non-local games, which is quantum information. The other is from the perspective of quantum groups. I'll briefly show a very cool graph theoretic characterization of quantum isomorphism and then get to the main topic of the talk, which is to construct graphs, finite graphs. Their automorphism group is trivial, but their quantum automorphism group is not trivial. And I'll show you the highlights, the big ideas of how to do that. Right. So first, quantum isomorphisms, quantum automorphisms. So we define a quantum permutation matrix as a matrix with entries in a C-star algebra such that the rows and columns sum up to 1 and all the entries are projections. Yes, thank you. So an example here, if we take just two projections in any C-star algebra, you can build things like this, very, very simple quantum permutation matrix where the entries are not commutative, and that's going to be important later. And I'll, oh no, wait, I have to give the definition first. So, okay, we work with graphs that are finite, undirected, and simple, so there's not self-loops at any vertex and there's no parallel edges. And then we write the adjacency matrix. It's a 0-1 matrix where the xi-th entry is 1 if there's an edge from x to I and 0 otherwise. And we note that classical isomorphisms are characterized by permutation matrices such that if you conjugate by the permutation, it takes one adjacency matrix to the other. Or equivalently, AXP equals PAI, AY. And based on this, we define a quantum permutation in the same way, or a quantum isomorphism, sorry, or a quantum automorphism. It's a quantum permutation matrix that intertwines the adjacency matrices. Or in the case of isomorphism, it intertwines like from the adjacency matrix of X to itself. Now we saw an example actually in the previous slide. I'll leave it as an exercise for you to check that this is a quantum automorphism of this graph. Where the vertices are labeled like this. Okay, so if we take our C-star algebra for the quantum permutation matrix to be just complex numbers, then this is exactly classical isomorphisms of the graph, because the entries need to be projections, 0 or 1, and the condition that the rows and the columns sum to 1 means that there should be exactly one in each row and each column. Yes. Yes, so because... Yes. So in MNA, where A is the C-star algebra, it is invertible because it's actually a magic unitary, it's sometimes called. It's a unitary because the rows or the columns summing to 1 mean that these entries are orthogonal projections. And so if you multiply by its adjoint, you're going to get the identity matrix. Yeah. Yeah, so it's a generalization of permutations to a non-commutative setting. Now, in the coming 2 parts, I wish to argue that this is the right generalization. So we start by the quantum information theory viewpoint, so non-local games. In a non-local game, it's an information theoretic procedure where Alice and Bob play a game with the referee, and they need to convince the referee of something. So the referee will send questions to Alice and Bob, questions X and Y, and they respond with answers, A and B. And there is some winning predicate for the game. So some set of tuples of inputs and outputs that are correct, and then the tuples that are not in that set are rejected, they're incorrect. So in this game, all the rules of the game, so the input sets, the output sets, and the winning predicate, they are known to all parties, but Alice and Bob cannot communicate during the game. They can agree on a strategy beforehand, but during the game they cannot communicate. And we typically play 1 round only of the game, and so 1 set of questions, 1 set of answers. And then we distinguish different strategies that Alice and Bob can use. So if Alice and Bob can make use of shared randomness, but only classical randomness, then that's called a classical strategy. And if Alice and Bob make measurements on their own part of a shared entangled pair, that's called a quantum strategy. And yeah, Alice and Bob want to play the game and maximize their winning probability. So I'm going to be focusing only on perfect strategies where they win with certainty, 100% probability, but there's this whole literature where you also study like the quantum value of the game or the classical value. Right. So example, the Mermin-Paris magic square. This is a very well-known thing in quantum information theory. So here we have the game where Alice is asked one of the 3 rows, and Alice should answer a 0-1 assignment to the variables in that row that sums to 0 mod 2, whatever the row is, and she only needs to assign the variables that occur in the row. Bob gets asked one of the 3 columns and should give a 0-1 assignment to the variables in that column that sum to 1 mod 2. And the winning condition is, okay, their answers need to satisfy the equations, like 0 mod 2, 1 mod 2. And there's exactly 1 variable where they overlap, and they should agree. Their answers should agree on that variable. Yeah, so you can show that there's no perfect classical strategy for this game, because basically you show that every perfect classical strategy would have to be a convex combination of deterministic strategies, but there is no deterministic strategy for this game because there's no satisfying solution to the entire linear system of equations. So that way you show that there's no classical strategies, but actually there's an operator solution where X and Z are the Pauli matrices. And these are order 2 self-adjoint operators that anti-commute. The tensor product, I guess you know what a tensor product is. So if you put in this, I cannot point with this thing. If you take a 2x2 square in the upper left corner, you have X tensor I tensor Z, I tensor X, Z tensor I. It's obvious that these operators commute pairwise, and you complete the first 2 rows and the first 2 columns. You complete them by putting the product or the inverse of the product, as everything is order 2. And so, yeah, I don't. Okay, so the first row, it multiplies to the identity by the way we constructed it, and the second row similarly. Okay, actually for the first column we put a minus sign, and the second column we put a minus sign in the entry, so they multiply to -1. And then it turns out if you put there xz tensor xz, it'll, because x and z anti-commute, if you multiply them one way around, you get +1. If you multiply them the other way around, you get -1. And this gives you an operator solution to the linear system, if we think of the linear system as being written multiplicatively, I guess. And you can turn this, by some quantum information, you can turn this into a perfect quantum strategy for the game. Okay, I guess here I have a slide about correlations, and I won't say too much about this. So just that there's different ways to formalize what a quantum strategy is. So in this setting, for instance, we take the measurement operators for Alice and Bob are tensor products. So each, like Alice and Bob, have their own Hilbert spaces, and the operators they use are tensor. Like Alice only uses operators on her space, and Bob only on his space. So the combined measurement is going to be a tensor product on finite dimensional spaces. But there's also this other commuting operator model, where you don't assume that they're working on a tensor product, but they're working on the same, measuring on the same Hilbert space. But the assumption is that all of Alice's measurement operators commute with all of Bob's measurements operators. For a long time, it was not known, can we approximate, like if we take the closure of these finite dimensional tensor product strategies, can we then approximate every quantum commuting strategy? And also for a long time, it was known that this question was equivalent to Kahn's embedding problem. So separating these correlation sets is known as Chilson's problem, and that's a deep and important question in quantum info. And I think they also use this connection the other way around to actually get non-constructive counterexamples that we now know for Kahn's embedding problem is via these non-local games. But I won't say more about that.
So what do you mean by
Yes. Yes, and yeah. So there's some. I guess I will be working in the quantum commuting model. So there's some Hilbert space and some state on that Hilbert space, some fixed state psi. And Alice and Bob have their measurement operators that commute with each other, but not within itself. Like Alice's operators don't commute with each other, but each of Alice's commutes with each of Bob's. Yeah. Yeah. Okay. So then for graphs, there's the isomorphism game. And whenever we define quantum versions of graph parameters, this is the way to do it. You turn it into a non-local game, then allow quantum strategies, and there you have your quantum version. So for the isomorphism game, we're going to build a game that models isomorphism. So it's a one-round game. Alice and Bob are each asked a vertex in either of the two graphs, and they need to respond with a vertex in either of the two graphs in such a way that their answers are consistent with an isomorphism, but only locally. So by this I mean here. So first bullet point, if Alice is asked a vertex in X, then she must respond with a vertex in Y. And if Bob is asked a vertex in X, then Bob must respond with a vertex in Y, and vice versa. Second bullet point, if Alice and Bob are asked the same vertex, they must respond with the same vertex. And if Alice answers with Bob input vertex, then Bob needs to answer with Alice's input vertex. Third condition, if Alice and Bob are asked adjacent vertices, then they need to respond with adjacent vertices in the opposite graph. And if Alice responds with a vertex that is adjacent to Bob's input vertex, then Bob needs to respond with a vertex that's adjacent to Alice's input vertex. So only these three conditions, this is the winning predicate. And then Lupini, Manchinska, and Robertson showed that This characterizes both classical isomorphism and quantum isomorphism in the sense that I defined before with the quantum permutation matrices. So there's a perfect classical strategy if and only if the graphs are actually isomorphic, and there's a perfect quantum commuting strategy if and only if the graphs are quantum isomorphic. And I guess you can also do the quantum version for the other models of quantum info by restricting the C-star algebra. So to get a quantum approximate quantum isomorphism, you need there to be a quantum permutation matrix where the entries live in a Kahn-embeddable von Neumann algebra. And to get a finite dimensional quantum strategy, you need entries in a finite dimensional C-star algebra. Yeah, okay. And so since we'll be working in the quantum commuting setting, I will denote quantum isomorphism with this QC here. Okay, so there's actually examples of non-isomorphic graphs that are quantum isomorphic. So this is the example. Somehow you take your Mermin-Paris square from before, you take those equations and you build a graph from that linear system in a way that's similar to the CFI graphs that Anna showed in the pre-seminar. I think it's not quite the same construction, but it's very similar in spirit. So you have some, in this case, you have some vertices that encode the equations, and there are edges if like the local assignments to the variables are consistent. There will be a different construction later on that I will get into more detail, but just Atserios and all those guys, they showed that the Mermin-Paris square gives rise to two graphs that are not isomorphic, but they're quantum isomorphic, precisely because the linear system had no classical solution, but it had a quantum solution. So quantum isomorphism is actually distinct from isomorphism. Okay. Now quantum groups. Some of you will be more familiar with this. So just, I guess, a brief recap. Okay, quantum groups, you can view them as deformations of Lie groups. You can view them as superclass of groups that allows you to extend Pontryagin duality to non-abelian groups. And you can also view them as the quantum symmetry objects of spaces in non-commutative geometry. And I will be focusing on the last viewpoint. I guess for Anna, brief recap on non-commutative geometry. I guess we start with the viewpoint of non-commutative topology. So if we have a locally compact Hausdorff space omega, then Gelfand duality shows that we can, there's like a correspondence between the space omega and the C-star algebra, the commutative C-star algebra of continuous functions from omega to the complex numbers. And then we define a non-commutative locally compact Hausdorff space to be any non-commutative C-star algebra. And now the space itself, omega, that doesn't really exist anymore, but you still have the algebra of functions on the space that you can do things with. This is the starting point of non-commutative geometry. And you can define structure on top of that to make it, in this case, a group. So there's some co-multiplication operator now on the C-star algebra, and that makes it into a quantum group. Okay, it's a basic proposition. Can I actually see a view of hands? Like, who here is not familiar with quantum groups? This one, okay. I'll briefly go through this. Yeah, great. Yes, good. Okay, so I guess I have time to, yeah, that's all right, yeah. So if we start with a classical compact group, then it's a proposition that you can recover the group structure completely from this co-multiplication map delta from C of G to C times G, C cross G, where the co-multiplication, it's like the adjoint of multiplying somehow. So right? We take some function on G and we need to turn it into a function on G times G. How do we do that? Well, by precomposing with multiplication. But actually, if you just remember the C-star algebra and this co-multiplication operator, you can recover the structure of G completely. And I guess that's sort of the motivation why we define a compact quantum group like this. So there's a unital C-star algebra and a unital star homomorphism delta from A to A tensor A, where the tensor now actually it's not the bare tensor product of vector spaces, but it's the C-star algebra tensor product, specifically the spatial C-star algebra tensor product. So there's some completion going on there. And it needs to satisfy properties that are like somehow the adjoint of the properties of group multiplication. So you need to have co-associativity, which is this first equation, and then some kind of cancellation property, which is the second one. I won't go into too much detail here. There's just a proposition is that if you have a compact quantum group where the C-star algebra is commutative, then actually it's isomorphic to the thing we defined above. So there's some actually compact group such that A is isomorphic to the C of G, and also delta is the same as the delta I gave above. So some examples of compact quantum groups. First is the dual of a discrete group. So if we have some discrete group G, the quantum group dual of G is the compact quantum group G hat, where the C-star algebra is the group C-star algebra. So it's a C-star algebra generated by unitaries for each element in the group. So if you've seen a group algebra, this is like a C-star algebra completion of the group algebra. And the co-multiplication is this kind of diagonal looking map. So you send UG to UG tensor UG. If G is abelian, then this is just the Pontryagin dual of G, but viewed as a quantum group now. So this is extending Pontryagin duality to non-abelian groups. Second example, also going to be important for us, is compact matrix quantum groups. So we have some unital C-star algebra A generated by like a square of entries in A, Uij, such that if you put these matrices with these entries, then these are actually invertible matrices in the C-star algebra of n by n matrices over A. And this map delta here that sends Uij to this like co-product somehow, it defines a unital star homomorphism. If these two properties are satisfied, then A comma delta is a compact quantum group, and it's called a compact matrix quantum group. Okay, so the quantum automorphism group of a non-commutative space is it's this categorical definition. There's a terminal object in the category of quantum groups acting on X. So it's like saying it's the largest thing that the largest quantum group that acts on the space. I'm not going to say now in this talk what an action is of a quantum group. And then, since this is a universal property, if the quantum automorphism group exists, it's necessarily unique up to a unique isomorphism. The question is, for which spaces does it exist? And Wang in the 90s showed that the finite set of integers 1 up to n, it has a quantum automorphism group, the quantum symmetric group, and it is the compact matrix quantum group generated by a quantum permutation matrix, as I showed on the first slide. So this is the second motivation that quantum permutation matrices, as I defined them, are really the right quantum generalization of permutation matrices. It's because it's actually the entries of the quantum automorphism group of an n-point set actually look exactly like that. And then building on this, Theo Bennica defined the quantum automorphism group of a graph. It is the compact matrix quantum group with the extra relations now. So we have these first two relations from the quantum symmetric group. And then the extra relation is that U commutes with the adjacency matrix. So this will give you a quantum subgroup of the free symmetric group. And that we call the quantum automorphism group of a graph. Actually, I should note that Bichon, not you, Bichon also first actually came up with a different definition. And the definition turns out to be different because he modeled the action differently. So Bichon also modeled there to be an action on the edges. So you get a quantum permutation matrix for the vertices and a quantum permutation matrix for the edges in such a way that they're compatible. And it turns out that this forces, if you just look at Banneker's view, this forces that certain Uij commute. Specifically, if there's edges I prime and J prime, then Uij commutes with Ui prime, J prime. So you get a quantum subgroup. It's usually denoted Q star X. It's not very commonly studied anymore because we like the bigger one mostly. So usually we work with the Banneker's quantum automorphism group.
You're not talking about the matrix. And the first line you were actually started with the matrix. You're not talking about the matrix, you're talking about the generator.
Yeah. Yeah. Yeah, so, okay, so yeah, I guess I'm saying two things in one here, but if you want to know what is the C-star algebra here, then it's a C-star algebra generated by Uij subject to these relations. And then the matrix is also Uij, but yeah. 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 And I guess maybe I don't know how you guys feel about this, but I read that some people found it surprising back in the 90s that classical objects have like non-classical quantum automorphism groups. I'm used to it because, yeah. Yeah. Yeah, but so certainly finite sets and graphs have very interesting quantum automorphism groups. And it turns out that graphs particularly, because finite sets, there's like kind of not enough structure, but graphs have enough structure to do really interesting and weird things, such as constructing asymmetric graphs with quantum symmetry. But that's why graphs are now very popular as like a way to find interesting examples in non-commutative geometry. Okay, so we motivated that quantum isomorphism is the right notion. I want to show one further connection, just very briefly, not get into details, where you have a purely graph theoretic characterization of quantum isomorphism. And this is like the main theorem of the field. So we count homomorphisms. Hom G, H is the number of graph homomorphisms from G to H. A graph homomorphism, it's a function on the vertex set so that adjacency is preserved. But non-adjacency does not have to be preserved, but adjacency has to be preserved. If edges are adjacent, then their image must be adjacent. In particular, because we work with graphs with no loops, this means that if vertices are adjacent, they cannot be mapped to the same vertex because there's no edge. So a very simple example of graph homomorphism is a coloring. Graph colorings, like proper colorings, are the same as homomorphisms to a complete graph on C vertices, where C is the number of colors. This is saying adjacent vertices must be mapped to different colors, and otherwise there's no constraints, because if you do that, then everything will end up at an edge, because it's a complete graph. So here we have this Hom set, but we only count the number of homomorphisms. Unlike Hom sets in algebra, there's no extra structure you cannot multiply to homomorphisms unless it's from the graph to itself. Otherwise, you cannot multiply or add them. So there's no algebraic structure, just a number of homomorphisms. And the classical theorem of Lovaas is that two graphs are isomorphic, G and H are isomorphic, if and only if for every graph F, the number of homomorphisms from F to G is equal to the number of homomorphisms from F to H. This is not a trivial theorem, even though if you look in the textbook, the proof is very short. But this has led to a lot of research where we get notions of equivalence of graphs over some family F, where we now look not at all graphs, but we only look at homomorphism distinguishing from certain graphs. So we say that G and H are F isomorphic if the number of homomorphisms from F to G is equal to the number of homomorphisms from F to H for all F in this class F. And we have combinatorial characterizations of various such notions. So, okay, if we take all graphs, then we get isomorphism. If you take only forests, so like disjoint unions of trees, then you get fractional isomorphism. If you take graphs of tree with less than or equal to k, which is an important parameter in structural graph theory, you get graphs that are indistinguishable by the k-dimensional Weisweiler-Lehmann algorithm. If you take cycles and paths, you get graphs that are cospectral and cospectral complements, meaning their adjacency matrices have the same eigenvalues with the same multiplicities. So all these natural like equivalence type relations can be characterized by homomorphism counting. And then Mączynska and Robertson showed that quantum isomorphism is characterized by homomorphism counting from planar graphs, which is just a bizarre statement because planar graphs is like one of the most natural classes of graphs, very important in graph theory. And somehow it has something to do with this quantum isomorphism. And yes, so a graph is planar if you can draw it in the plane so that edges are like paths in the plane that do not intersect. So you can draw any graph in the plane with intersecting edges. The point is to avoid intersections. Yeah. So yeah, so okay, this graph is planar. Famously K33. Maybe I should have specified that there's a vertex there. Yes. That could have been clearer. So if you take a complete bipartite graph with 3 vertices on each side, this is famously not planar. There's no way to draw this without intersections. And like a famous theorem in graph theory is that every graph which is non-planar contains either this graph or K5 as a minor. So some kind of subgraph. Yeah. Okay, and so actually this proof, okay, so as I was saying, it's already spectacular that we have a purely graph theoretic description of quantum isomorphism. You're just counting homomorphism from planar graphs. There's no quantum anything going on. But what's even nicer, and you'll appreciate this, is that actually the proof uses representation theory of quantum groups. So the representation theory of the free symmetric group is actually much simpler than the representation theory of the symmetric group. It's just some kind of non-crossing partitions. And that is where the planarity comes from somehow, like the non-crossing. So if you're non-commutative, you get string diagrams where strings are not allowed to cross, and that's what makes things planar at a very high level. The proof is a lot of combinatorial details, but somehow in my mind, this is where it's coming from. Right, so won't say anything further about that because I want to get to asymmetric graphs with quantum symmetry. So various authors who worked on quantum automorphism groups have asked questions along these lines, like what is the maximum disparity we can have between the automorphism group and the quantum automorphism group? So for instance, can we have that the automorphism group acts intransitively, but the quantum automorphism group acts transitively? Okay, so there's actually a notion of quantum orbits. I'm not going to define them. Actually, I will define them. It's very simple. I didn't put them on the slides though. So you can define two vertices are equivalent if and only if uij is not zero in this quantum automorphism group. And you can show that this is actually an equivalence relation. I don't remember how you showed it. Yeah, so we take our graph, and the quantum automorphism group is these quantum permutation matrices that commute with the adjacency matrix. Then you define two vertices to be equivalent, or yeah, they're going to be like in the same orbit, if and only if uij is not zero in the quantum automorphism group. And then you can show that this is an equivalence relation, so it's transitive. And so the orbits are like the equivalence classes of this equivalence relation. And classically, right, if you think of just permutation matrices, this is exactly saying there is a permutation that maps I to J. Now this is
You can do that.
yeah, but okay, but uij is now like a universal, so it's the generators in this quantum automorphism group. So before in the first slide I showed the definition of a quantum permutation.
It's not the IJ of quantum permutation.
The one with the relation. You can choose multiple of them and then like try to get rid of all the additional relations that might hold.
Yeah, so you look in the universal C-star algebra. Yeah. Yeah. So this is the uij in the universal C-star algebra, so in the quantum automorphism group. And that's the universal one. And then every quantum permutation matrix is a homomorphic image of that universal one. Okay, so the question was, is it possible to have an intransitive automorphism group with a transitive quantum automorphism group? Other question that has been asked, can we have a trivial automorphism group, non-trivial quantum automorphism group? Or can we combine them even? Can we get an automorphism group that's trivial and the quantum automorphism group acts transitively, which is at the far opposite? So the first was answered in the positive by Lupini, Manchinska, and Roorsen. The second will be the topic of the talk today, and the third question is still open. And the goal for today is to show that there exists a graph X with trivial automorphism group, non-trivial quantum automorphism group. So this is the main technique. I think if there should be one takeaway from this talk, it's going to be this slide. So we do something like the Mermin-Paris square, but with a twist. So first we call the Mermin-Paris square. We have a linear system of equations. So it's an inhomogeneous linear system over the field of two elements. There's no classical solutions, but there exists an operator solution, and it's this one that I showed before. Now to get asymmetric graphs with quantum symmetry, we're going to do something similar. But now we're going to look for a homogeneous linear system, mx equals 0 over F2, that has no non-trivial classical solutions. Obviously, it's always going to have the zero solution, but that's going to be the only one. And it has non-trivial operator solutions. And that's somehow going to give us what we want in a way that I will show you in the following slides. So it's really like, think of it as a homogeneous version of Mermin-Paris. Okay, so here's a foolproof outline. We start by finding some linear system. From that, we look at the homogeneous solution group. I will say what this is. And then we construct a colored graph, which has the dual of that solution group as its quantum automorphism group. And from that, we go to an uncolored graph with the same property. And I will say what all of this means. Okay, so first, what is this colored graph? So now a colored graph is a graph X together with a vertex coloring. And I'm not assuming that it's now a proper coloring. So adjacent vertices are allowed to have the same color. It's just any function from the vertices to some set of colors. And the quantum automorphism group of the colored graph, now we add this extra relation here that vertices with different color are not mapped to each other. So the colors are kind of like forcing orbits to be smaller. So example, if we take the complete graph with all vertices black, so all the same color, then the quantum automorphism group is just this free symmetric group. If we take the Peterson graph, graph theorist's favorite, then actually Simon Schmidt showed that its quantum automorphism group is classical. Okay, color graph. So here we have a square with two red vertices on top, two blue vertices on the bottom. Now what we're saying is that every automorphism or quantum automorphism needs to respect the colors. So the only classical automorphism that you have here is the reflection about the y-axis. And actually you show that also the that's only the only quantum automorphism here. Maybe I can briefly mention that we have, together with Petter Zeman and my other co-authors from Denmark, we have a paper where we compute quantum automorphism groups of trees. And there also this color thing comes in useful because you want to color the roots differently and then proceed by induction down the tree. So it's a technique we use sometimes to compute quantum automorphism group, is coloring things even if you started with something with no colors. Yeah, I just put the C for color to clarify that I'm looking at the color preserving quantum automorphism group and not because otherwise I should have written X comma C. Because X is just a graph. Yeah. I should have said C as well, yeah. Yes, good question. Right, so we have our colored. This one? Yeah, so then we get a bigger automorphism group, but also we get we get that the quantum automorphism group will now be non-classical. It's gonna be, okay, so we take the complement, then we have the disjoint union of two edges. And for disjoint unions, we get the Reeve product, I think, if I recall correctly. So it's disjoint unions of isomorphic graphs, then you get the Reeve product. If it's disjoint unions of non-isomorphic graphs, then you get like the C-star algebraic free product. Not the group theoretic, but yeah. Yeah, it's going to be infinite dimension. Yeah. With just 4 vertices. Yeah. Okay, so solution groups. These are just classical groups. So if we have some homogeneous linear system mx equals 0 in n variables over f2, we define a group valued solution to be a tuple of elements of some group H, that it's going to be locally a solution somehow. What do I mean? I mean, okay, the H1 up to Hn have order 2. And if you look at each equation in your system, so each row, and you look at the entries that occur with non-zero coefficient in that row, those Hi or Hj, they commute and they multiply to 1. This is saying that kind of like these Hj that occur in this ith row, they satisfy the equation. Of course, we need to multiply instead of add now because our group is not abelian, so we need to write everything multiplicatively. So we're just saying like in each equation, the variables commute and multiply to 1. And then we define the homogeneous solution group to be the finitely presented group with generators H1 up to Hn subject to these relations. So you get some finitely presented group that encodes all group valued solutions of your linear system. So solutions in some group H correspond to homomorphisms from the solution group to H. Okay, now we come up with this construction. Let me immediately go to the example. This is again a CFI-like construction, but it's not quite a CFI graph. Now we built a bipartite graph from our linear system that will have the right quantum automorphism group. So what do we do? So here's an example. We take our linear system to, three variables, two equations. For each variable, we make two vertices on top, corresponding to a 0 or 1 assignment for that variable. And then for each equation, we make vertices. We make vertices at the bottom for each equation that correspond to valid assignments, 0, 1 assignments to the variables that occur in that equation. And so for instance, here we have x1 plus x3 equals 0. There's two valid 0, 1 assignments to the variables that actually occur there. So I write them as 0 question mark 0 and 1 question mark 1. And here we have an equation where more variables occur and we get more vertices. So here we get 4 vertices. And then we add edges so that every equation vertex has an edge to each variable vertex that it agrees with. So we have 0 question mark 0, so it has a 0 in the x1 position. We connect it to the 0 vertex for x1. Here we have, I don't know, we have a 1 in the x2 position, so we connect it to the 1 vertex for x2. This is really encoding your linear system as a graph. And then we make it a colored graph by giving different colors to every variable, like the two vertices for each variable, we give a separate color, and the 2 to the k vertices for each equation, we also give them separate colors. And now the idea is that the quantum automorphism group of this particular graph is actually going to be isomorphic to the quantum group dual of the solution group of the linear system. And the classical automorphism group is going to be, okay, the abelianization of the linear system, but that's just isomorphic to the kernel of the matrix. And okay, so intuitively, at least classically, intuitively, you can sort of think of, okay, an automorphism that preserves the colors. So on each, on top, for each variable, you can either be the identity or exchange the 0 and 1 for that variable. And then it turns out that the only like combinations of exchanges on top that extend to an automorphism also at the bottom and with the edges are the ones that are homogeneous solutions to the linear system. So think of it as like kind of like saying if we have an automorphism, it's doing something on the variable vertices. If we write what it does, no, that's not what I want to say. So somehow what I'm just trying to convey is that no, never mind about this. I cannot, I don't think I can explain it right now any clearer than this. It's just a graph that encodes the solutions of the linear system somehow. Right. I guess here I wrote what it's going to do, but I'm not, no, let's skip that. Okay. So we have for each colored, okay, this is the second step. Okay, so we now have a colored graph where we can control the quantum automorphism group, but we want to turn it into an uncolored graph. So we give some kind of decoloring procedure. This is purely combinatorial and works for all graphs. And we show that for every colored graph, there's an uncolored graph with the same quantum automorphism group. Quite standard, I would say, in computer science to do things like this. So we replace the colors by some gadgets. For instance, the gadgets can be paths of different length. You want to make sure that your gadgets make it so that so that these orbits are fixed. So you want to have different gadgets, that one gadget cannot be mapped to another gadget by the automorphisms. Yeah, okay, and then in the quantum setting, it's trickier to show that actually the gadgets work. So maybe not everything you can do classically works in a quantum setting, but we show that there's some way to do these gadgets so that you decolor and the quantum automorphism group is preserved. Right? So this gadget, for instance, is gonna, so this is the only vertex of degree 1 that has such a long path of degree 2 vertices before it reaches something of higher degree. And you show that this is then preserved by automorphism and by quantum automorphism. And actually the tool you use for that is the one-dimensional Weisfeld-Lehmann algorithm. And you show that this vertex is distinguished under one-dimensional Weisfeld-Lehmann from all other vertices in the graph. And so in every quantum automorphism, it needs to be preserved. And then it follows that these also need to be preserved. And this class needs to be preserved as a whole, but it can be permuted. And that way you show that all the colors are preserved. Okay, now we are left with the following test. So for every linear system mx equals b, we have a graph x m comma b, where the quantum automorphism group is isomorphic to the dual of the homogeneous solution group, and the automorphism group is isomorphic to the kernel of M. So to get asymmetric graphs with quantum symmetry, what we want to do is find a matrix M with trivial kernel and non-trivial homogeneous solution group. Okay, how do we do that? Well, okay, you try some matrices. Compute what is the solution group. Well, I mean, it's a finitely presented group. Asking whether or not a finitely presented group is trivial is in general undecidable. I think it's also undecidable if you only restrict to solution groups even. So that doesn't work. I mean, we asked Gap actually, but it just ran for a month and nothing. You need to be more clever, you need to come up with a good trick. That's what we did. So again, the goal is find a matrix M so that the kernel is trivial and the solution group is non-trivial. Now we're gonna start working from some target group H, and we build a system from H. So we look at all the solution group relations in H. Recall that in the solution group we had commuting entries that multiply to 1. So we're going to look at all elements of order 2 in H. For each of them we get a variable xh of the linear system. And then we get an equation like this. If you have some triple, h1, h2, h3, they pairwise commute and they multiply to 1. So from your group, you search all elements of order 2 and all these 3-element relations between them. And you turn that into a linear system with one variable for every element of order 2 and one equation for each relation, then by definition, you have a group valued solution to your linear system. You can put xh equals h, right? So this variable that we created for h, we put it equal to h, and then it has a solution in h by definition. And so in particular, whenever h has an element of order 2, the solution group is going to be non-trivial. So now we just need to check what is the kernel of this matrix that we get out of this. You start trying some small groups, compute the matrix MH, but then you find out there's a lot of small groups, like particularly groups of order 2 to the k. There's a lot of them. But then we notice that actually we only need to look at perfect groups, so groups whose abelianization is trivial, because otherwise the solution group is also not going to be perfect. And there's actually not that many perfect groups, so we just tried a bunch of perfect groups and we found out that the alternating groups, they work. So if you take n at least 7, I guess below that it's too small to work somehow, then the alternating group an has, so this kernel of the matrix that we get is trivial. The solution group is non-trivial by definition, because the alternating group has elements of order 2. And then we get what we want. So we have solution groups with trivial, non-trivial solution groups where the kernel of M is trivial. So if you put this all together, we get asymmetric graphs with quantum symmetry. So here's a recap. We start now with the alternating group AN. From that, we built a linear system. This is going to be a system with 105 variables and 140 equations. So my computer likes it, I don't. From the linear system, we then construct a colored graph where the quantum automorphism group is isomorphic to the solution group, and the automorphism group is trivial. And then we decolor and we get an uncolored graph with the property that we want. And actually, not just one, we get an infinite sequence of them. So, great. That's what we want. So, yeah, it's almost the end of my talk. I just want to leave with this open problem. We don't know how to do this. Is there a graph with trivial automorphism group and where the quantum automorphism group acts transitively? Now you may ask, like in this construction, what do we need to change? What properties of the solution group do we want? But actually, this construction can never give us that, because an essential step in the construction was to use these color classes and then add gadgets. This is gonna, we're now locked in, aren't we? Tomorrow morning, I suppose. Yeah. So, yeah, so our construction uses these color classes to force certain orbits. And even after decoloring, the orbits are still forced. So our construction is never going to be transitive, and we need a completely different idea. Somehow the hope of this question is that it will give us new insights into quantum automorphisms of graphs. Like how can you find Cayley graphs or something? Actually, the people who work on quantum graphs tell me that you can do this with quantum graphs, but I'm not too familiar with that. There, I would like to end. Thank you for your attention.
Questions for Josse?
You're not getting out.
So you said that if we took, what was it, Kn, then the quantum automorphism group was the quantum symmetric group.
Yeah.
And you said also the representations of the quantum symmetric group are quite simple. Yeah, you said they're partitions. So in general, can you say what the representations, the co-representations of, can you relate the co-representation theory of the quantum automorphism group of a graph to the representation, to the graph itself, or something like this? Can you describe the co-modules of the quantum automorphism group of a graph?
I can't, but I mean, it seems plausible that something like this might be possible. Yeah, actually, I don't know if people studied this.
You know, it's a compact quantum group, so you have Peter-Weyl decomposition. So every co-module appears inside there as a summand. Whether or not that helps, I don't know.
No,
I guess there's not some general principle to describe these things that you know of anyway.
no, not that I know of.
Yeah.
No.
But for what? For the symmetric group, for the free unitary? Yeah, that was my next question actually. Is the free unitary group, does this arise as the quantum automorphism group of some graph?
No. I don't know. Yeah, so the unitary group. It's probably a reason why it doesn't, but like also you don't get the, or maybe that's actually the reason, because then like the abelianization of it would be the unitary group. I don't think there's a graph that has the unitary group as its automorphism group, because automorphism groups of graphs are finite. So the obstruction, I think, is that if you take the abelianization of the C-star algebra, that should be finite. And that's not satisfied for the free unitary group. Actually, there's a whole study of like the Frucht property. So a theorem in graph theory by Frucht says that every finite group can be realized as the automorphism group of a graph. Every finite classical group can be realized as the automorphism group of a graph. And it's known that not every finite quantum group is the quantum automorphism group of a finite graph. Yeah. But I guess like, maybe I get my definitions wrong, but I think there's even uncountably many subgroups of Sn+. There's only countably many finite graphs. But J.P. McCarthy and Theo Banneker, they actually gave specific examples of groups for which they showed that they don't have the Frucht property. And I think the dual of A4 or A5 was among them. And we show actually, our computations show that the dual of A8 can be realized as a quantum automorphism group. So but this is something people are studying, like which groups can we get? And I think with quantum graphs, they can do every finite quantum group as a quantum automorphism group of a quantum graph. But for graphs, it's not very well understood which groups you can, or quantum groups you can and cannot get. So, okay, the free unitary group is not one of them, but there's a lot of them where you can ask me the question and I don't know. This one.
Yeah, so looks to be like the data name of our graphs, the third statement. No, I mean whatever. So can I keep the direction? I mean, if I say two graphs are going to be isomorphic and only the number of homomorphisms from my, okay, so from any other graph to these graphs are same. I believe, can I switch the direction?
Yeah, it's still true if
It is
it's still true if you switch f comma g, like if you take g comma f, h comma f. Yeah.
and what
But-
about the definition factor generalizing?
Yeah, somehow that has not received the same amount of attention, I think. Yeah, I'm not aware of any notions that have been studied that way, like the opposite way. But it's also, no, I don't think. Like I don't think, for instance, even here, I don't think two fractionally isomorphic graphs have the same number of homomorphisms to every forest. I don't think that's true. So I think you would get different isomorphism notions. And I'm not aware of them being studied, but maybe I just didn't look at that part of the literature.
So on one side, we don't have any eminent expected, but on the other side, you have a like C-star algebra. How this C-star algebra is coming? I mean, if I start from this picture and if I'm going to the other side, how this C-star algebra is coming?
I don't think I know enough of the proof to give a concise answer or any answer. Yeah.
Use.
Great.
Sorry, I couldn't hear you guys super well. I guess my question is just, has anyone really tried to look at directed graphs, like keeping all the other assumptions, finite vertices and no parallel edges and stuff like that? Because that could allow you to sort of make an interesting, maybe definition of quantum isomorphism of things like Kuhn-Krieger algebras.
I think I've probably seen some papers where they also do connected graphs, or people do hypergraphs, people do all sorts of things, but I'm not too familiar with that literature. I think somehow most of the focus is on the graph setting. But I am aware of a paper by Simon Schmidt and Moritz Weber, where they study quantum automorphism group of graph C-star algebras. And they connect it to the quantum automorphism groups of the graphs.
Okay. Cool. Thanks.
Any other questions from the others? The last one that we like gene spaces. And so I guess that would reduce that to quantum solvents. So you have graphs, there's some way to produce subjective dense level subjective groups to the other uses.
Yeah, so I don't remember what we were talking about back then.
So I'm interested in quantum spaces.
Mhm.
Joule for quantum groups, quantum subgroup is just going to be surjective orthogonal map from one compact quantum group that space and what's called. You see way but two graphs. Or you buy a graph, so graphics. If you have a graph, you have to see ways of surjective.
Yeah. So I see why coloring would be an example. But just like by definition, right? So where did I put the quantum automorphism group of a colored graph? Yeah. It's just you're adding one relation to the universal C-star algebra. So there's yeah. Yeah, this is new. The rest is for the quantum automorphism group of an uncolored graph. Yeah.
Suggestion and look for covariance, which is what the finance and trying to figure out.
Yeah, because I also I'm not so familiar with all of the Hopf algebra terminology. So if you maybe we can work through an example. Like if we just take one vertex and color it differently, then your quantum automorphism group is going to be the stabilizer of that one vertex. So what would now be the invariance, even classically? I guess you're not used to thinking about like these concrete automorphism groups. So, yeah. We also have a paper where we compute quantum automorphism groups of lexicographic products of graphs. The lexicographic products, you take, I always forget what you put inside. So I think you take some. So for every vertex in X, I think this is going to be the lexicographic product X, Y. For every vertex in X, you make a copy of Y, like disjoint copies, and then according to the vertices in X, you either put a complete bipartite graph here or nothing. So say if X was a 4 cycle, then you get and there we proved the quantum version of a theorem of Sabidusi, which shows that the quantum automorphism group of this lexicographic product, under certain reasonable assumptions on X and Y, it's going to be the free Reeve product of the quantum automorphism groups of X and Y. Now I'm thinking, does the free Reeve product surject onto one of them? I would imagine it does, but then I guess you can also, if we take, no, yeah, like maybe if we take each copy, yeah, okay, so maybe we can color the vertices of this lexicographic product in such a way that like different copies of the same vertex get the same color and different vertices get different colors. And then, so this, I guess, is a special case of coloring, but I think you would get a quantum automorphism group of X now as a subgroup, so the quotient on the algebra level. I'm not sure if anything interesting comes out of this. So.
Thank you so much again. The very next talk. Next week.